All right. So welcome everyone to this week's webinar. So my name is Jean-Philippe Gagnon, and I'm a field application engineer at Telops. So today we have two speakers, Stefan Buganga and Justin Buczynski. Stefan from Telops and Justin from Trilion. They will talk about synchronous full field strain and temperature measurement. Our first speaker today is Stefan Buganga from Telops. So Stefan received his PhD degree in condensed matter physics in 2008 from Montpellier II University in France. He worked as a researcher at the Los Alamos National Labs in New Mexico in the US and an associate professor at Tohoku University in Sendai in Japan. Since August 2017, he is working as a field application scientist for Telops in Paris in France. His research interests include infrared thermography as well as infrared and terahertz remote sensing. So, Stefan, you have the floor.
Yeah, thank you all for attending. I will try to keep this within 15 minutes talk. Um, uh, Starting by saying a few words about Telops. Telops is a company founded in 2000 in Quebec City. We are about 93 employees, including PhDs, masters, and engineers. Telops headquarter actually is in Quebec City, but we also cater an international market using offices in US and in France, where I am currently located. We also have an efficient global network distribution and representation, and we have over the years built a wide partnership for thermography-based EOM solutions. For instance, for digital image correlation, Trilion integrate our cameras in ARAMIS Trilion the DIST software and allow to propose a full turnkey thermography and deformation testing solutions for material analysis. In the next few slides, I will discuss basic notions of infrared imaging and our product lines and features, and also discuss some examples where our high-speed infrared cameras were used for material testing. As you all know, all objects over 0 Kelvin emit infrared radiation. The amount and maximum of the emitted radiation actually follows the Planck law, as you can see shown here for different temperature here. The higher the object temperature is, the higher will be the emission intensity here. And some portions of the electromagnetic spectrum, I mean long wave, mid wave, and short wave, and so on, are also displayed there. If you look at this curve here, the blue one at 300 Kelvin here, room temperature, you can notice that the emission intensity is very low here in the mid-wave infrared as compared to the long wave infrared here. This tells you that for the same pixel size here, long wave infrared camera will be very good for room temperature based application, and mid-wave and short-wave infrared will be very good for hot target. But we'll show you here that we can propose mid-wave infrared cameras with a wider pixel and small quantum wells for very good also for room temperature applications here. Normally at a thermal equilibrium, object will absorb infrared radiation and remit that infrared radiation, and that self-emission is actually what the infrared camera sensor collect for infrared imaging here. And for a broadband camera, the signal is usually measured on each pixel is usually a sum of all contributions of all objects in the field of view there and over the all focal plane array detector spectral range here. And another important thing worth mentioning here is the emissivity. The signal measured by the camera mainly result from two contributions. Here can be the emissivity variation or temperature variation in the scene there. And the emissivity actually describe the material inherent characteristics in the thermal infrared here, and the temperature contribution here is described by the Planck law I discussed one slide back. And usually high reflective material will have a very low emissivity, and black body will have emissivity close to 1. And in experimental mechanics experiments, usually samples are quoted with high emissivity painting to get close to the black body configuration here. And also in digital image correlation, this notion of quoting samples is actually omnipresent here. And our cameras are calibrated with a black body assumption. That means that the temperature reading is called radiometric temperature here. And once those the data are collected with that radiometric temperature here, our software offer multiple radiometric correction features such as emissivity correction to obtain absolute temperature here when the emissivity weakly varies with a wavelength, as you can see here in case of a gray body and a black body. But sometimes emissivity can or strongly vary with wavelengths, but this is another story. In this case, spectral informations from the cameras are needed. Now, I will say a few words about our product lines. Here we design and manufacture high performance and high-end infrared cameras, and our cameras we usually like to classify them in 4 different categories here. Those 2 here are spectrally resolved cameras, and those one are broadband cameras. This one is a hyperspectral cameras. This one you have here, it's a spectrometer inside there combined with a camera. These are multispectral cameras with fast rotating wheel filters here. And the broadband cameras, this one will mostly be of interest in mechanical, in experimental mechanics here. High-speed cameras in our fast model here with up to 120,000 frames per second. The fastest infrared camera in the market here, and it also combines high definition capabilities. And also high dynamic range categories, which allow continuous acquisition from 0 to 2,500 degrees Celsius. Now, we have been doing infrared camera business for 20 years now, and recently starting to include in our product line integrated systems with our cameras, and those integrated systems include active thermography solutions called tested here for a wide variety of applications. We can offer from a wide range of solutions, from basic systems, as you can see here, to more compact and integrated systems with a variable level of automatization depending on customer needs and constraints. And for other integrated systems such as digital image correlations, we have partnership with Trilion, as you will see in this webinar today. We produce infrared thermal imaging systems with good spatial resolution. We design and offer infrared lenses, as you can see here, from midwave extended from 25 millimeter to 100 millimeter here. We also design and offer microscope lenses here, G1X or G4X here, as you can see here with a spectra with a partial resolution somewhere in between 30 micron to to few micron, I want to say, depending on the pixel pitch here. So to summarize here, we offer infrared cameras from short-wave infrared to long-wave infrared from zero point 0.9 to 12 micron. Here we propose broadband cameras and spectrally resolved cameras. In the spectrally resolved cameras, we can have spectral resolution up to 1.5 nanometer there, and multispectral cameras also. And for interest for experimental mechanics, we offer broadband cameras with high temporal resolutions, the fastest infrared cameras in the market with up to 120,000 frames per second here. Using those cameras here for digital image correlation is very ideal, since the cameras in those digital image correlation systems, those visible cameras are very fast, so you need an infrared camera that goes fast too. We offer cameras resolution from QVGA to VGA format, HD. We even now offer Super HD format here, and as I discussed, very high spatial resolution down to 2.5 micron per pixel in case of mid-wave camera with 4x length here. And now very quickly some examples showing the benefits of high-speed infrared cameras here in experimental mechanics. The inelastic deformation behavior of practically all material is known to be affected both by strain rate and temperature, and it is well known that material typically will release heat when they undergo alteration because of that elastic and plastic deformation. And a common way of characterizing materials, as you know, it consists of establishing this stress and strain curve here, which reflects the behavior of the overall sample after microscopic level here. And during those experiments, sometimes the transitions from one regime to another here can be very fast here, and high-speed infrared camera can be very useful here for properly characterizing the whole process here. This show an example of a tensile test carried out on a steel sample with our M2K camera here at 4,350 frame per second here, and the video you see here allow to visualize the result as a function of time. Time is shown here. And in the next slide here, these are some selected images during the experiments here, corresponding to different stages of a typical stress-strain curve there. And the time labels you can see here illustrate how fast the sample switch from one regime to the other one. Here 1.3 millisecond, here 0.2 milliseconds here, and highlighting the need for a high temporal resolution in this kind of experimental testing here. This is an example where our high-speed infrared cameras were combined with a visible, high-speed visible camera with a dichroic mirror that which was placed somewhere here to experimentally measure the deformation and the temperature field simultaneously for the dynamic loading experiments at the microstructure level here. The sample structure is shown here with the field of view of the visible and infrared cameras with the temporal resolutions shown in the here. And here is some image obtained with the two cameras there. Simultaneous visible and infrared images here allow, for instance, to locate those hotspots you can see here in respect to the microstructure feature here. And identification of the location of those hotspots can be very important in this case, for example, for understanding the mechanism underlying the formations of those hotspots here. For example, a hotspot inside of a grain like this one here and far from interfacial boundaries most likely will result from inelastic deformation, while a hotspot at the boundary here will likely result from frictional dissipation here. And note again here the temporal resolution here, which is 0.2 milliseconds here, highlighting the need of high fast infrared cameras here. This is digital image correlation result obtained there with the temperature fields here and the strain field here, allowing to study those free hotspots here at 1 milliseconds and 1.2 milliseconds here. It was seen in this example here that the temperature increase in the hotspot from 1 to 1 milliseconds accompanied by an increase in the shear strain here in the hotspot, and a conclusion that the two measure mechanism here in the materials are plastic deformation and frictional and the frictions here, both of which result from shear deformation beyond a certain limit. This is the last example I wanted to show where our high-speed infrared cameras were used with visible camera in a digital image correlation configuration to analyze hotspot generation in a composite material and a polymer with inclusions of graphite. And what you see there are infrared videos showing the sample deformation induced movement of those solid inclusions and temperature increase. Please notice again here the temporal resolution here of 50 microseconds, which correspond to the camera speed of 20,000 frames per second here. And the digital image correlation showing strain fields and temperature field here, where the axial strain in the polymer region between the solid inclusion is very significant compared to the other locations in there, and the shear strain on locations is high on location where the temperature is high here. This suggests that high shear deformation near those solid inclusion cause relatively high motion between the polymer and the solid inclusion, which causes the heat generation and the following temperature rise. So those are some examples of work we have done on collaboration with researchers and scientists. Here you can find those papers in the literature there, but beside that intensive work in there, we have partnership with Trilion in digital image correlation to bring you a turnkey thermography and deformation testing solution for material testing. I will stop there to hear more from Trilion and hand back the mic to Jean-Philippe. Thank you for listening.
Yeah, thank you very much, Stefan. It was very interesting indeed. So now let's switch over and let me introduce our next speaker, Justin Buczynski. He's a technical account manager at Trilion. So Justin is the, as I said, technical account manager at the Trilion Quality Systems Great Lakes Regional Office. The Great Lakes office is on the campus of Lawrence Technological University, where it supports the civil engineering department. Justin graduated from Ferris State University in 2007. Justin has been working with in the automotive-related technology field for 7 years and uses his previous experience in the field of secondary education to build relationships in higher education, research and development, as well as manufacturing industries. Justin lives in the Detroit area with his wife. He enjoys camping, kayaking, and when he's not consulting on engineering equipment.
Yeah, thank you so much, Jean-Philippe, for that nice introduction. So now it's my job to introduce you to ARAMIS 3D optical strain. And directly after, we'll be demonstrating ARAMIS 3D thermography and exploring our partnership with Telops a bit further. So stay tuned. I work for Trilion Quality Systems, and our 3D digital image correlation device, ARAMIS, featured here on the screen, provides an unparalleled quantitative view of deformation and failure all along the surface of your material or your part. And what's more is that it provides a rigorous method to verify and validate model predictions. Trilion is an American engineering firm that's been in business for the last 22 years. We specialize in the development of optical 3D measurement and analysis tools and helping our customers with application development, consulting services, and turnkey system deployment. We have a large market presence, as you can see, across industries with over 600 systems deployed in North America alone. Trilion is the exclusive North American testing distributor for GOM, a Zeiss company based in Germany, and GOM develops the software and the industrial systems for the industrial 3D coordinate measuring technology, 3D computed tomography, and 3D testing. Today we'll be focusing on the 3D testing tool ARAMIS that is indispensable when monitoring and analyzing the development of displacement or strain fields in time. This is the deformation analysis tool, ARAMIS. It includes hardware and software designed together. It's a pair of cameras and a blue light. ARAMIS uses a principle of triangulation between its two cameras to identify and track points along the surface. ARAMIS users place stickers on the surface of a testing object. Each sticker becomes a 3D coordinate for point tracking in the time domain to get 3D velocities, 3D accelerations, and with creation of local coordinate systems, you can get the inspection of the 6 degrees of freedom. ARAMIS can also use stochastic pattern on a surface to create thousands of tiny dots that the software divides into subsets for tracking strain, both principal and directional. A subset of grayscale pixels in the reference image, representing the zero or initial state, is matched and tracked dynamically to a similar subset in the target image of the deformed state. In the resultant full field strain data on the right, you can imagine placing down a conventional foil strain gauge at a point that maybe your model had predicted. You'll miss the full story told here by ARAMIS because we're not limited to discrete points, although we can give those. The zones of higher strain are easily identified and studied. ARAMIS delivers higher quality data for materials testing that's unmatched by clip gauges or strain gauges. It can be used to replace your traditional sensors that suffer from imperfect attachment to the measured surface. And because ARAMIS uses stickers or just spray paint for preparation, it yields more data in less time, about 100 to 1,000 times more data, in fact. And so test labs love ARAMIS because it empowers them. They don't have to worry about missing areas of inspection or future iterative testing. They can simply go back to their already recorded images and see their full part under load. And this serves as a bridge between the simulation and the test lab. And directly connecting these two improves your products. For displacements, ARAMIS is now certified as a class 0.5 extensometer or a class B1 extensometer according to ASTM standards. ARAMIS measures shape, displacement, strain, speed, velocity, rotations, quite a few things there, all in a non-contact way. So we apply to many different testing groups, as you can see here. In material testing, ARAMIS is a versatile measuring tool. Any shape, any material, any temperature. And so we're going to focus on tensile testing today for our demonstration. But as you can see, we apply to many more applications. Just wanted to have everyone see some of our applications there. Circling back to the pattern is optimized to be random, isotropic, highly contrasting. Sometimes customers get worried about this. You can see, even if you accidentally spray a big black dot, as you can see on the left image, we've actually gone back and repaired the pattern with just some white speckling over the top. Quite simple to do. The software will recognize the pattern, divide it into a triangular mesh that you see on the right. You see that pink mesh. Look for that pink mesh there. Each node of that mesh represents a discrete location where we can pull strain data, both principal and directional. And so the spray paint becomes thousands of strain gauges across the surface. Here's a quick video of just that process and how it's done. We can do many samples at once. Often customers do 10 or 20 at once. We spray down a light coating of white and then release the pressure on the nozzle of the black flat paint, just aerosol off-the-shelf paint, and we're able to speckle pattern many different samples at once. We also feature stamps and rollers, even a printer that can print on pattern, but here with just spray paint, it's very quick. You get that cookies and cream looking pattern, and now we've got all our samples set up, and we can bring them to the load frame. Loading the tensile coupon into the load frame, we're now able to see all across the sample a 3D full field measurement. So ARAMIS is agnostic of material. It's going to capture the strain propagation even in the high strain or the necking area. And as you can see on the right, the ARAMIS technology has a very high sensitivity with an ability to see flow fronts of the material. And from this data, we can determine automatically the material parameters. When synchronized with the load history data from the testing apparatus, ARAMIS data can be configured to automatically plot the stress strain curve, and we'll find parameters according to your standards, ISO, ASTM, whatever they might be, including N value, R value, Young's modulus, Poisson's ratio, yield strength. Often we're assuming constant volume here for, say for instance, R value, but many other material parameters as well. In aerospace and automotive testing, we see ARAMIS being used for testing of high-performance composite materials, commonly used in structures where high strength and stiffness are required at a minimum weight. Here you can see the longitudinal strain along the surface that reveals those composite reinforcement fibers. Polymers and laminates are also big use cases for ARAMIS. ARAMIS captures even high strain, and here's an impressive data set with a polymer. ARAMIS continually tracks the subsets of that pattern throughout the project. The system is independent of temperature, as I mentioned before, and can see through a chamber window to make strain measurements such as this tensile test of magnesium at 300 degrees C. We can go upwards, up over 1400 C in fact. And we do account for the distortions of that glass. ARAMIS works great for comparison to simulation. It looks and feels like FEA software already, but it is full field 3D reality. To go a step further, the ARAMIS has the capability of overlaying the simulation with the real ARAMIS measurement to provide deviation maps. If you look at this wrench here, you see in the bottom right-hand corner an example where this overlay is incredibly intuitive to understand. You can see the areas where it deviates and point to those hot spots. So with a single iteration, ARAMIS users update their models to be ever closer to reality. Here are some things to consider for ARAMIS. It measures optically and has a seriously fast setup. It can change its field of view with lens just by changing the lens or even just changing out the bar that's used. It gives you data all across the material part, including the necking area. It captures strain, displacements, accelerations at the same time. It's independent of material or temperature. It can capture static or dynamic, utilizing the latest in high-speed cameras. ARAMIS features also a rigid body motion compensation feature that corrects for any global motion in your project, so you can bump the cameras and still get a good measurement. It also interfaces well with test machines, so you can synchronize everything together all at once. And so that's our introduction to ARAMIS. Let's now jump into ARAMIS 3D Thermography. One of the many add-on Python scripts integrated with ARAMIS is our ARAMIS 3D Thermography. It involves the combination of IR and ARAMIS. An IR camera with trigger synchronicity is linked to the ARAMIS, and the temperature data can then be brought into the ARAMIS software and mapped across the specimen's surface in a common 3D coordinate system. That means bringing in the temperature data and putting in 3D coordinates. You can sort of see that here. On the left, you can see our setup for this demonstration we're about to provide here. The Teleps Fast IR M3K camera was positioned just off to the left of the ARAMIS 3D optical strain sensor to the right. And they have similar fields of view. So on the right side of the screen here, you can see the results from each sensor. I'm now going to turn things over to Joe Horn, our engineering manager, for a walkthrough of our ARAMIS thermography.
Hello everybody, and welcome to the demonstration portion of the webinar. I have opened the ARAMIS professional software with a tensile test experiment. The objective of this demo is to not only show the functionality of the ARAMIS software, but also show how easy it is to integrate thermal data, specifically from Teleps. The material of the sample here is steel, and the load frame was set to pull the sample at 8 millimeters per second. Both the ARAMIS 2.3 megapixel system and the Teleops M3K camera are set to record at 450 frames per second until the sample broke. Additionally, the Teleops M3K camera was set to trigger off of an input signal from the ARAMIS system with a BNC connection, so the images between the two data sets will match up perfectly. So now in the software, I'm going to scroll through the timeline you see on the bottom, and you'll see the image automatically update. These are all the images that were recorded for the duration of the test. Then the part breaks right there. So now I'm going to go back to my initial image, then I'm going to define my surface with the surface component function. It automatically looks for the stochastic pattern that you see on the part and identifies the surface. Here with the current parameters, I have about a 3 millimeter size strain gauge. The software is easy to use, and I can quickly reduce that down and make my strain gauge about 2 millimeter size. Depending on the type of test you're running and the type of results you want, you can quickly change the settings there. So now to illustrate the amount of data points I get across the surface with my settings, you can see here the mesh structure. This shows all the data points and all the virtual strain gauges I can get. You also may notice that there are some jagged edges across the part here. I can clean up these edges just by using the deselect polygon tool. So I'm going to outline the part here and clean up those edges. And then once I'm done, I'm going to right-click and finish. These little boxes here are facets, and these are what's used to being identified the surface there. That's just a little close-up of the mesh structure. And then when I do the image overlay back on, I'm going to then go ahead and create my surface component. Then once I'm done that, you may notice that there are also dots on my part. We'll get into why they're there in a little bit, but it operates in the same function on how it's looking for an ellipse there. And then I can just highlight all the points that I want, automatically detecting the size. So I have the 6 points, and I'm just going to name it dots. I create that. And then I'm going to let it calculate throughout the entire project. So then it's going to match each image and track the changing of the surface throughout the entire project. Once it finishes computing, I can then go ahead and scroll through the timeline again, and you can see how the software is tracking that surface. Even without the image on, you can see the 3D structure elongate and strain throughout the project. Now what I'm going to do is I'm going to run the thermography script. This is embedded in each professional version of the software, and I run the first one, and then what it's going to do is going through all the images and seeing how many images there are throughout the entire project. Once it finishes, a window will pop up, and it's going to ask me, do I want the relative temperature change or the absolute? For this project, I have the absolute temperature. I then select the files I want to import. Now, in this folder that you see here, this is all the ASCII data exported from the Teleops software. I choose the very first file, and then I enter in the parameters of the camera. In this case, my focal length of the lens was 50 millimeters, and the pixel size, which is the size of each pixel on the sensor, is 30 micron. Each ASCII file is going to have all the radiometric temperature data associated with each pixel in the image. Now you can see here, it imports the first image from the Teleops software. And now what I'm going to do is I'm going to use those dots that I created to align the thermal image on top of the ARAMIS image. So I'm going to do this 5 times, and I'm going to control click on each dot. The first dot I'm going to control click is on the thermal image, and then I'm going to control click the associated point in space on the ARAMIS image. So I'll do my first 3 dots at the top, then I'll move to the bottom and do my remaining 2 clicks. So you can really see here how the dots light up like a Christmas tree, in the Talops software. So it makes it really easy to identify the two. Now, when the 5 points have been associated to each other, I then get a deviation of 0.5 pixels, which is great, and you can see the overlay of my mesh on top of the thermal image, which shows me how well it's aligned. And if I wanted to do a realignment, I can simply do that. Now it's matching the thermal image from that list that you saw for importing to all the images inside of the ARAMIS system. Once the mapping of the thermal data is complete, I can start to take a look at the data. You'll see here that there's this temperature inspection, and when I recalculate it, you'll see that there's a color map of the thermal data overlaid on top of our surface there. The color map is associated with the legend on the right-hand side, and it's a dynamic scale. We aren't able to fix the scale, but the dynamic scale automatically updates the min and max of the legend as we scroll through the images. And you see a failure there where it gets at its hottest temperature. I can then plot a specific point on this surface here and see its change over time in the diagram. So I'll go ahead and take a look at the diagram now. And you can see there at that specific point over time, that temperature is going to increase and so ultimately fracture. I'll turn the image back on, and then we can start doing our normal inspections like we would in ARAMIS. Taking a look at the eye inspect here, you can see all the different options from directional strains to principal strains to displacements. However, we need to set an alignment first to make sure that our directions are appropriate. Going into the 3-2-1 alignment, I can define 3 points for my normal plane on the surface, 2 points for my axial direction, and 1 point for the origin. I'll go ahead and turn on the overlay, and you can see that global coordinate system overlaid on top of my surface mesh with the z-axis normal to the surface. My y direction, which is the green vector, is now axial. So with this, I can now do an appropriate directional strain check on top of the surface. So now with the epsilon y now inspected, it's now plotted over the surface. So now we're taking a look at the percentage change across the surface there. And remember, we have thousands of data points across this entire surface. So each point is like its own strain gauge. And now on the element tree on the left, I am toggling between the temperature and the strain values. So now I can see the correlation between the temperature and how much the surface has elongated. Running the thermography script again, I can then start to incorporate the temperature and the coefficient of thermal expansion of this material to extract any thermal expansion of the part and just look at the pure mechanical strains. So in here, I'm just going to say my temperature inspection on my surface is that temperature one that was automatically created by the script. Then I enter in the coefficient of thermal expansion for steel. In this case, it's 13. And then when I hit OK, it automatically creates all these inspections for me, as you saw populate in the element tree on the left. And I can toggle between them. Here you'll see epsilon y corrected, which is taking out any of the thermal expansion there. So now this is taking in that CTE data of the steel, taking in the thermal data, and then giving us a corrected, purely mechanical strain reading. I can treat this just like any other point there and plot a point in the center. And then in this case, I'll plot it for regular epsilon y, as well as the corrected epsilon y. And here I'll just enter in the particular values for the y as well as for the temperature. And then I'll enter in again the CTE of the steel. And now we're seeing on the plot both points being plotted simultaneously, as well as now the temperature plot at this specific point in time. Looking at the label here, you can see there's a very tiny difference between the two, probably because the temperature isn't very high but it is still adjusting it for whatever the temperature value is and the CTE. I can continue doing this for additional points across the surface and then start to create report pages and exporting the values there. Now looking at the overall mesh, you can see now the epsilon y corrected. I hope this software demo was informative and showed the power and ease of use when combining ARAMIS with the Teleps thermal camera. The high-speed nature of both systems allows us to gain insight into our parts with high loading rates and varying temperature gradients. This technique of high-speed thermography is not just limited to material testing, but can also be applied aptly in the automotive, aerospace, and microelectronics industries. Thanks again for your time, and we hope to discuss this application for your testing needs.
Thanks, Joe. Great presentation. And Joe's right. Besides tensile coupons, this type of technology can be used in structures as well. And here's a hairdryer design test that inspects the temperature and the thermal expansion of its nozzle, compares it to the motor on the backside there. The graph shows a profile of principal strain led by the temperature data and the bottom diagram there. Other areas of ARAMIS thermography include engine and powertrain testing, and here's yet another, microelectronics. Understanding the bulging of chipsets has long been an ARAMIS application, but with ARAMIS 3D thermography, we can map the temperature data for added understanding. Customers that use ARAMIS with temperature data often bring in thermocouple data for further analysis. They encounter issues with attachment, conductivity. They often need to know ahead of time the position of the important temperature data, and they still don't have any real overview of the thermal behavior of their part. And yeah, they are going to risk a misplaced sensor as well. Whereas with the ARAMIS 3D thermography, there are many advantages. It's contactless, the data is collected in full field with a common coordinate system, and this yields an overview of the thermal behavior of the part or material and its relationship to deformation. The customer has 3D coordinate temperature points, and they can explore the project to better understand previously unknown effects. And finally, it is this unique 3D analysis of deformation and temperature in ARAMIS that allows for the decoupling of thermal and mechanical strains. So thank you very much. Appreciate your time today, everyone.
Yeah, thank you very much, Justin. Very interesting again. So it's nice to see how we can couple both the camera and this software evolution to really take full advantage of what the camera can provide. So we have many questions here. Yeah, so maybe this one is more for Stefan. So what is the lowest temperature that it can measure? So I guess I'm guessing the camera here.
Yeah, if we're talking about the camera, if infrared camera, we're really talking about infrared camera here. The M3K that was demonstrated here for DIC measurements, the lowest temperature depend on calibration, how your camera is calibrated. We can calibrate M3K, for example, down to minus 10 degrees. And go up to maybe 150 or even 200 degrees without any filters. Actually, I don't know if you have a constraint on the temperature of your setup actually, but yeah, we can have a broad range of temperature there, and also we can move toward a long wave infrared if yeah, it's depend really on your need, but we can accommodate quite a broad range of temperatures with our cameras, actually.
Yep, indeed. Yeah, thanks, Stefan, for answering that. Next one is probably for Justin. So what is the accuracy in ARAMIS?
Yeah, that's a great question. And so because we're non-contact, ARAMIS is going to be a lot more accurate than other conventional style sensors. And through a third-party study, we've shown to be approximately 10 microns within the true result and that's going to be a lot more accurate than other sensors you might have. But the term accuracy can often mean many things to some people. So with just describing its sensitivity is very dependent upon its field of view. And so at a full meter, 1,000 millimeters, where we have a sensitivity or noise floor of 2 to 7 microns. And as we come down in field of view, maybe say 100 millimeters, then we would have a sensitivity of 0.2 to 0.7 millimeters. And so that linear relationship exists between the field of view and our sensitivity. Furthermore, our precision should be considered as well. So when considering our precision, we have maybe a plus minus 50 microstrain when it comes to strain measurements. And so all this kind of maybe gives you a more full conceptual picture of what the ARAMIS is able to achieve.
All right. Yeah, thanks. I think it answers well the question. Maybe another one here. What coordinate system does your sensor use?
So when we shoot, we typically are using coordinate systems based upon CAD. If we don't have CAD, we're going to be using just a normal into the Z out from the page coordinate system, and then we will typically align according to the surface itself. You saw maybe the 3-2-1 alignment that Joe provided in the demonstration, and that's something we typically do with our surfaces to fit any coordinate system that makes sense for your measurement. But we often are aligning with other things, especially CAD or FEA, or in this case, thermography data, to put everything into the same CAD coordinate system or coordinate system. So that is something that is quite easily done. Hopefully that came across in the demonstration.
Yeah, thanks. Yeah, I think it did. Maybe the next ones are more for Stefan. So Stefan, could you please elaborate a bit about the microscope lenses that you have?
Yeah, the microscope lenses that I shown there during my presentation. Maybe I can share one slide. 3K, again, the camera that was with the M presented today for the DIC measurements here. We have few options here of microscope lenses. We can provide a G1X lens. Here this means that it gives you the spatial resolution of the pixel pitch, and the pixel pitch in those M3K here is 30 micron. That's when your spatial resolution will be 30 micron here. It's a quite good microscope lens here because it have a kind of long working distance, 260 millimeter here with a pretty decent depth of field here plus minus 1 centimeter with a manual adjustment here for that. And the image coverage is a microscope, of course, 2.9 millimeter times 7.68 millimeter. This is the microscope that was used in one of the DIC slide I showed you with those microstructure with a dichroic mirror here to see result after micrometer level there. We also can offer G4X lenses. Again, you divide the pixel pitch by 4 to have your spatial resolution. Here, the working distance is a little bit smaller, and also the depth of field, but also the image coverage here. But again, if you have a project in with those Microsoft lenses, we can discuss this offline and give you some more details. I'll give you back the the
presentation, but that's okay. Thanks.
presentation.
I don't.
Okay.
Yeah, since we have a lot more questions, but I think time is running out. It's almost 3, and it's an hour-long webinar, so I guess we should probably stop here, fortunately. But as I said, everything is logged, and our speaker today will spend some time to answer all of you and get back to you with a document containing all of your questions answered. So again, I'd like to just take a few moments here to thank our 2 speakers today. I think it was very interesting. So thank you a lot, Stefan and Justin, for being here and for doing this webinar for us today.